Welcome everyone to this inaugural kickoff session for our Digital Data Flows Masterclass series. I'm Christopher Kuhner. I'm a professor at of law at the VUB here in Brussels and also co-director of the Brussels Privacy Hub, which is a research institute at the VUB. I'm here briefly to just introduce our institution and what this is about, and I'm going to turn the floor over to Jules, who will tell you a lot more. As Jules said, there are a number of people also observing this remotely, virtually, so welcome to all of you as well. The idea of this was, I think, to explain technology in a way that non-technologists could understand, which is something that's sorely needed. When this event was announced, I got a number of emails from people saying, "Oh, I'm looking forward to your presentation." Well, I have to be honest and say, if I were trying to explain technology, I would be guilty of gross negligence because I don't understand it myself. So I'm looking to be enlightened myself here. I think we all recognize that talking about data protection and privacy nowadays without an understanding of some of the important technological elements and some of the underlying technologies can often be a futile endeavor. So we're very grateful to Dr. Gupta and Dr. Grau for coming to talk to us. I also want to thank very much FPF and Jules Polonetsky and all of his team, Stacy and Gabriella and others, with whom we're very happy to have a very fruitful collaboration now for several years, and I think we will continue to collaborate in this series. So I'm going to now turn the floor over to Jules, who will tell you a bit more about the event. Thank you.
Thank you, Chris, and thank you for your partnership with the VOB. So you won't hear too much from the lawyers because many of you certainly at the conference heard plenty from lawyers. I think Chris's point about all of us who do law and ethics and policy need to understand technology has probably never been more extreme when it comes to issues like machine learning and AI. Someone can teach us a little bit about how apps work. But most of us, and we don't need to be coders to debate whether we think advertising is operating in an ethical way and many of the really important topics. It's very hard to have a serious conversation about machine learning issues and the ethics of AI and issues like explainability and fairness and bias without understanding a little bit more than even most of us who work or like technology are able to do. Most of us don't have the statistics backgrounds, and when someone talks about linear regression, we think of, is that with the X's and the Y's? And here we're supposed to tell companies, make your technology fair, and what does it mean for bias and the like. So we've got two phenomenal experts who we've brought over from Germany and from Georgia. I'll tell you a little bit about them. But before we launch in, this is the first of what will be 8 programs, and we've picked the technologies that we think regulators, policymakers, everyone who needs to interrogate this sort of technology need a bit more. We will do our best to not talk law and policy. There are probably different views, and there are people who maybe are waiting to even make up their mind about some of the issues. And so our goal here will be to ask technologists to explain, and in a way that maybe is not as accessible. I've been trying to get smarter and watch various online courses and so forth, and they're very much geared towards teaching you to run and code and manage these technologies. And we don't need that. We don't want that necessarily, but we actually need to understand where is the personal information here, so we've tried to design these to elucidate the kinds of questions that those of us who care about questions around personal information can have answered as these presentations are geared up. So if you made it today and this is new and you're interested in signing up for all 8, they will all be remote, so you can do them from home, from your pajamas. We will have a number of in-person ones just because it is nice to see people and so forth, but it's designed so that you can participate completely. VUB is partnering to even provide a certificate so you can feel like you are achieving something of some educational value in addition to interesting and applicable. Okay. I'm really delighted to have one of the leaders in very practical applications of machine learning who understands where we are coming from. For those of us in the policy world, Dr. Oliver Grau works for Intel's R&D department in Germany on automated driving, on validating AI systems. He has published more than 70 scientific publications. He holds more than 10 patents. His PhD from Hanover University. He is a active member of the ACM Europe Council, visiting professor at Surrey University in the UK, and really plays a lead role for the ACM in technology policy issues, so really is living at the intersection of some of these issues, and we look forward to an education from him. I'll introduce Professor Gupta after we hear from Dr. Grau. So the floor is yours, and thank you.
Yep. Thank you. Yeah, actually, thank you for the nice introduction. Actually, I think you really got the kind of gamut of things I'm doing. So I'm an engineer. I'm a trained engineer, but I work for Intel, which is apparently a big company in the IT business. But I'm also chairing the ACM Europe Technology Policy Council, and this is actually where all this technology, that's one of my motivations in this role, where this technology intersects with society. And it's quite challenging today to have 20 minutes to go over artificial intelligence, because artificial intelligence it's a huge topic. But maybe I can at least give you here and there a few things you might know already, but you now see some other aspects in it. And I hope we can also expand this later in a discussion. So what is AI? I said it already. AI is a very complex scientific topic. It's actually, you might also see it's consisting of several disciplines in science. And today we see there are many new sciences like data science is a topic 20 years ago was not present. So artificial intelligence is something very quickly evolving, and it has already a long history. So I put here down two definitions of artificial intelligence. The first one is from a quite famous textbook from the 80s, 90s. And actually I used this textbook when I was at university. And this is just one attempt what AI is or might be. It's trying to enable the computer to do things in the computer that only humans can do otherwise. But what that means, it's pretty much a moving target. And you see also from the second definition, very similar. It's also about cognitive functions and what cognitive functions are. I'll go over this in a second. But in the second definition, over time, the learning aspect has become much more important. And that is actually what happened in the last 20 years. So 20 years ago, we had attempts to do AI. And this was mainly done with kind of discrete programming languages. So we had expert systems and things like this. And it didn't work very well. And what followed was is coined also the winter of AI. And what made AI working in the applications we see today is machine learning and deep learning with neural networks in particular. So AI is a big subject. If you look into textbook, scientific textbook, you can hardly find a textbook. You might have a series of textbooks. And there are the more classical, mathematical, statistical-driven methods like regression and clustering and all of that. And what became very popular in the last 10 years, it's in the middle, it's deep learning. And that's based on neural networks. Interestingly, here again, neural networks are not new. They were used and described already in the 60s. But what is new is, or what made them work, and what was a problem in the 60s at least, and even in the 80s, was that we have now, because of progress in technology, we have much more capable machines doing these learning processes, and we were not able to do that 10 or 20 years ago. And the second ingredient is data. I mentioned this already. So reasoning, here it's a bit underrepresented, but there is still a large body of systems that also up today have their place, like rule-based reasoning systems. They are not completely dead. And in particular, with many applications, we kind of get a feeling now where the limits are of the neural networks. And I think we will also see some hybrids in the future. So AI, as we know it from textbooks, still has its places in many different applications. This is kind of a view from the applications, and it also it answers a little bit what might be a cognitive process, because that's also hard to define in a few sentences. So cognitive processes. Some people say it's in general what thinking is about. That's some people compare this with cognitive processes. Mathematically, or from an application point of view, what we do with AI today is we try to give data some meaning, and this is analytics is a big topic here. And there are just various aspects to analytics, from hindsight, insight, foresight, forecast, self-learning. So this is just a kind of axis of what you might want to do with AI. I'm not going much further into the span of applications. Instead, I want to give you a few examples of how AI works. Some of them you might know, because you are coming from statistics, for example. Some you might not know, but it's just to give you a rough feeling what it is about. So what I call a building block is classification. Classification is part of recognition processes. For example, here I've chosen the example of fruits. So you take out a fruit of a fruit bowl, or moreover, you want to program a robot to take out the right kind of fruit you're interested in. So the task is to decide, is this the right fruit or not? And in order to do so, you need to classify what kind of fruit it is. So that's called classification. So here in this very simplistic example, I've chosen two different fruits, an apple and a banana. And one way to do a classification, it could be done by linear regression, or equally here, what is also the model underneath linear regression is a linear separator. And this is also the simplest neural network we know, which is called a perceptron. I haven't looked it up here, but I think these perceptrons were introduced in the 60s. So it's a very old concept. And yeah, now how you set the parameters here. First, you need to extract some features. That's the classical approach. I called it x1 and x2 here. So for example, in this case, you might just use the width and the height of the fruits. Yeah? And if you're lucky and you have chosen the right features, you end up with something here on the right, which means the bananas are somewhere in this diagram, which is just a plot of the two parameters. And the apples are in a different area. And with a linear separator, you can now separate them out. And the linear separator gives you, or classifier gives you an answer. I've chosen here 0, 1, which is the digital or computer domain, but it could be also yes or no. And everything below the line is a no, and everything above the line is a yes or 1. In this case, it's the banana. So this is there are several methods to determine the parameters, and in the terms of neural networks, I will give you an example in the next slides how this could work. But it's a numerical minimization process. And here's the line is found usually by fitting it to the data. And here's the first problem, and that's if you have now sampled your data wrongly. For example, if I have sampled more bananas, and at home, for example, I would expect that some people in my family, they would choose not the brown ones because they don't like it. So you might end up with a different characteristic every time, depending on how you choose your data. And this is one of the causes, numerically, for bias. And we will have in the next talk by Swati Gupta, she will go more deeply into these kind of problems. So one way of dealing with the problem here, the first line should have disappeared. I just go forward and backward. So you see the second line is on a slightly different position. And here, one example is now in the wrong class. Of course, what you could do is you could use a higher order function to describe it. And that's actually what is done with multi-layer neural networks. So you see here, just as on the top examples, multiple of these neural cells, if you like. And with multiple of these in multiple layers, you can approximate any higher order function you like. Still, you have the problems fitting the data correctly and choosing the data correctly. But that's in a nutshell how neural networks work. So, and again, these examples I've just shown, they are old. They were well known in the 80s, 90s already. So what's different now? Because there's now, I would almost call it a hype about artificial intelligence. And there's one term coming up very often. It's deep learning. So what's deep learning? What is it different to the things we have seen before? Fundamentally, it's just you have more layers in your neural networks. And what it does technically, if you compare it with the, let's say, classical methods in computer vision, and I have done a lot of work on computer vision, recognition of license plates or whatever. Typically, you start, if you start from images, you might also start from other sensors, but if you start from images, you choose your features, and you build a detector that is extracting some number according to a feature you set scientifically. And a feature might be the distance of my eyes, it might be the ratio of your head and other things. And traditionally, that was done by an engineer or a scientist. And then you apply some classification algorithms on top of that. So what's new now with deep learning? Deep learning is basically starting from images and ending with the classification. And everything in between is done by machine learning. Also, the let's say the finding what the right features are. There's, however, a problem, and I come to this in a moment. That is the features might not tell you as a human being anything anymore. It's just a number. And that's also showing here why deep learning became so popular. In computer vision, that's the science that deals with images and give images an interpretation. We had in the 80s, starting 80s, 90s, we had several competitions where databases were built up with standard classes of objects. And there were competing universities building systems, computer vision systems, that are best in recognizing these classes. So from 2010 onwards, deep learning was introduced on these databases. And suddenly, and you can see here on the left, the error rate went from 30% almost down to what is now better in some cases as a human. And this is significant. And this is also, people say this is a hype about deep learning. There's no debate. Deep learning networks are better than anything we have known until 2010 with conventional techniques. And similar results were achieved in speech recognition. So that's why deep learning is so important. And deep learning also gave AI a new inertia, and that's interesting to understand. Because the downside is now people have slightly over-inflated expectation from the rest of AI. And that is a real problem. Just because in this one discipline, deep learning is really best choice of tools. Does not mean AI is the best choice for everything. Yes, this is just to give you a glimpse of how the learning works, but I'm probably starting to run a bit out of time. What was the timing? Where's Drew? No timing constraints, so I carry on. So just learning works with examples, and it's usually if it's supervised learning, it basically propagates back errors. So in other words, here if you have a bicycle and it's recognized as a strawberry, you get an error, and from this error you learn numerically, and you adjust your network in an optimal way. It's a mathematical optimization. And that means if you have the right data and the right approach, you get an optimal result. That's the good thing with deep learning. If you have now trained this, you apply this, and this is called inference. So what are the challenges? And that's something it might be more familiar to what you are doing. So in the introduction, Jules mentioned I'm working on problems of automated driving. So automated driving tries to achieve what most of you probably can do. It's driving a car, but completely automated. So we assume we will have a lot of AI. I mean, even if it's not deep learning and deep networks, we have some components that you might consider as AI anyway, in a classical way. So the big question is it safe? And this is something we need to answer before we can introduce this as a product. And it's actually not good enough to have 10% accuracy. The mark is being better than a human driver. And this is something which is technically quite challenging. So there are a lot of issues how you make these things safe. Automotive industry, they have test procedures, but they all can't be applied because neural networks are not deterministic. So we need new metrics here. And also there are questions if you do something like what we call the driving policy, that's how the car behaves in traffic. Would you learn this, and from whom would you learn this? I mean, this is a good question, yeah? So there are still a lot of open questions. Understanding networks is one of the most popular in technical terms, because as I said, we have no standards to estimate if something goes wrong. We have no tools to analyze what goes wrong. So understanding deep networks, and here's one example. It's a paper from MIT. It's currently debated to use activation maps. So I mentioned you have no clue what features the network has learned, but with these activation maps, you get some feedback of areas, for example, that are activated in these maps. That's just one example. Societal challenges are a lot, and you are here coming together to discuss all these privacy issues, and that's, from my perspective, a very real challenge. So we have, in research, we have at the moment the problem we can't use any data captured in the public, even for research purposes. So we're developing these techniques, and they need data, but we're not allowed to use this data. This is a conflict. I don't think we should just lower our standards in privacy. We just have to find ways to match from a technical way, like privacy by design. I'm very much a fan of that. There are also things we discuss on trusted platforms and others to overcome these problems. Trust is for any introduction of a product a real problem. And a lack of understanding is something, yes, we can overcome. But there are also other issues like safety, security, and so on. Yeah, I'm just wrapping up. As I said, whenever I discuss this presentation, I find many things I couldn't put in the presentation because it was just 20 minutes. But basically, what made AI taking up again now is machine learning. It's neural networks. They're perfectly adapting to tasks. They outperform standard methods by far. But there are still a couple of problems, like how you cope with biased data, lack of explainability. One thing I didn't mention was adversarial attacks. I think these technical problems, they will be sorted out over time. So all the minus here in this list, I think we will find over time answers by science. What remains to answer are the societal challenges and commercial challenges. Unbiased data, we have the next presentation about that. Privacy, I briefly mentioned. And from a commercial perspective, if you introduce a product like an automated car, you have to solve three things. It's trust of the consumer, which should buy the car. You need regulation right, and you also need to get safety right, and these are interdependent. So that's almost it. One last hint. I was also a co-author of a white paper we wrote from the Europe Technical Policy Committee about decision making, which goes into more aspects of decision making with AI. Like ethical questions I have completely skipped. And in the interest of time, I say thank you here and open this up for discussion.
I think our plan is we're going to have Dr. Gupta present, and then we'll have questions in one collection so that our academics will figure out which is best to answer. So I thank you, Oliver. Our colleagues here are going to just switch over the computer for a second while I introduce Dr. Gupta. Before I do, in your packets is the Privacy Expert's Guide to Machine Learning. It covers some of this material, some of it in a little bit greater depth. We have lots of charts. We like our charts because I think for many of us, if you can see, you can better grab some of the concepts. So we've got some good charts. If you don't have it, it is online. And then there's another publication in the back aimed at companies and how they can do information governance around machine learning. Again, some copies there, and you can find it online. So flying over to us from Atlanta, Georgia, where she's at the Georgia Institute of Technology, one of the leading academies, leading computer science schools. We have Dr. Swati Gupta. She's the assistant professor in the Milton Stewart School of Industrial and Systems Engineering at the Georgia Institute of Technology. She has a PhD in operations research from MIT, and of course, dual degrees in bachelor's and master's in computer science and engineering from the India Institute of Technology in Delhi. And she's been doing some really interesting work from a mathematical and technology sense into issues like fairness and bias. So it really gives us an interesting flavor of how when we ask someone to examine data in a technical way from bias, we can do so. Are we set? Good? Dr. Gupta, please. Thank you for joining us.
Thank you. Hi, everybody. Thank you so much for inviting me here. I'm very excited to give you this talk. Thank you, Jules, and the FPF and VOB for organizing this session. I am, as Jules mentioned, I am a technical person, so you'll see, I guess, some more insight into what these machine learning models are doing and what are the bias and fairness questions we should be asking, where the tension in these questions lies, and who can we look to answer and give us some insight on how to solve these questions. So with that,
sorry, we have people on the other side of the Atlantic, and we are trying to share a screen,
okay.
which does not always work.
So how many people attended the main event at the European Parliament? A lot of people. What was the favorite quote on, can somebody tell me the favorite quote that they heard yesterday or today in the morning session? Any volunteer? Yes.
Yes, I'm Stewart for Privacy Laws and Business Reports, and I think the most important quote was, ethics tells you not what you can do, but what you should be doing.
Great.
That's an important point.
That's an excellent point, and I think this will also be what we see in the presentation, what we should be doing. And another quote that I really liked was from Tim Cook, saying that we need to decide what kind of a world we want to live in, and that's a theme I'll keep coming back to in this talk. So just a quick view of what's happening as in Oliver's talk. We have some data, and then we apply some machine learning techniques and algorithms to that. That's basically finding some pattern in the data, and then we use this pattern to make predictions and to make decisions for consumers and for users, for human beings. And the key question we want to ask is, what is the effect of these decisions on human well-being? That's the key question. And to lead this presentation, I wanted to take a quote from Nature, which is one of the leading journals, international journals of science, which identified bias as one of the 4 ethical priorities of neurotechnologies and AI. And I really liked the way they presented what bias is. When scientific or technological decisions are based on a narrow set of systemic, structural, or social concepts and norms, the resulting decisions or technology can privilege certain groups and harm the others. And I thought this was point-on definition for what bias is. And let's see some examples where some of the recent examples where we have observed unintended consequences of using data-driven decisions. For instance, Amazon was providing same-day delivery to all neighborhoods of Boston except Roxbury, which is a predominantly African-American neighborhood. And that created concerns, obviously. Rating systems have, in ride-sharing platforms like Uber, are known to feed back the bias from the consumers back into the system. So if you're riding a car with somebody who's from a poorer background and the car quality is not good, you give them a bad rating. And eventually the system rejects drivers who cannot maintain a good condition of the car. Oops, something happened. Okay. Maybe, sorry. Okay, thank you. Another example of Another example of unintended consequences, or probably in this case it was a bad choice, was that Facebook was letting advertisers exclude users by race. And this borderlines illegal activity when it comes to ads pertaining to housing, employment, education, and some of the protected domains in the US. Another example of problems with data is one where Google was mistakenly tagging African Americans as gorillas simply because it didn't have enough data on darker skin tones for doing facial recognition. Predictive policing is going to be one of the running examples in my talk that talks about how algorithms that are determining certain risk scores of criminals and defendants, how is that affecting the judge's decisions to release these people or not, and what are the potential ethical issues in this area. And the last example I sort of want to leave you with is automated experiments on ad privacy settings showed that Google was showing lower paying jobs to women. Okay, there were some messages on the screen. Google was showing some lower paying jobs to women at a much higher rate than showing those lower paying jobs to men. 6 times at a higher rate, these ads were shown to women, which is clearly problematic. All right, so the outline of my talk is going to be the following. I'm first going to highlight the bias in data, variables, models of machine learning. Then we are going to look at various definitions and ways in which one can define what's fair and what's not. And this is a place where I'm going to need input from all of you. And lastly, I will come to the problem of choice. It's the trolley problem of choice. How many people have heard what the trolley problem is? A few, okay, great. So let's start with the bias in data and models. And as I said, we are going to look at predictive policing, which is the application of analytic techniques to predict where future crimes might occur. So if you just focus on this image here, this is data from Oakland County, and the darker red spots are showing more prevalence of police arrest reports in the area. So you see that a lot of arrests were made in this region, and not many arrests were made in this region. This is the International Boulevard region. And what's happening here is that these methods, or this algorithm, is taking in the data, and it's looking at, let's come back to this figure. So it's looking at the data, and it's trying to find a pattern. This is what machine learning is doing. It's looking at the past police arrests, trying to find a pattern, and say that this is the pattern in the data, and so now I can predict future arrests. But a lot of the arrests, a lot of the crime incidents is missing from the picture. And so you don't see a lot of these blue points because the arrests are predominantly happening in that the area 1 in that region. And so the true pattern that your algorithm or machine learning should have learned is this one. But due to absence of data, because of collective bias, where police are going, they can only catch criminals at those places. Because of that bias, they don't see the full picture. I think
the reason you have the full picture there is that's data that includes
yes.
from the health, where is that border, the second data set from?
Yes. So great, yes. So this is what I'm coming back to here now. This is the police arrest data, but then Christian Lum and William Isaac in 2016 did this very nice piece of work where they put together other data sources from the National Health Survey on drug use and health, and they realized that actually the prevalence of crime is all over this geographical area. It's not just concentrated to where the police have made arrests. But now, as you can see, because of this collective bias in data, as we noted in this diagram, the model predicts very different trends, and it leads to over-policing in areas that police have already looked at. And this is something what any human would also do, right? If you see arrests in particular areas, you'll think, okay, these are unsafe, and police need to go here more. But it's just the absence of the big picture. You don't have the full picture. And so the model predicts that actually the prevalence of drug use is much higher in African American communities, but it's actually known to be approximately the same in the whites as well. And these problems with data are not just about collection. We live in a biased society, so no matter what data we collect, even if we have a large amount of data, there will be some bias fed into this data because of the actions we are taking as human beings. It's, to give you an example, this was a study done by researchers where they looked at various images, and some of these images showed cooking scenes. So images were about a kitchen and somebody is cooking in the kitchen. But most of the images had women cooking in the kitchen, so the machine learning algorithm learned a pattern that, if it's a kitchen, it's a woman. And it was not because there was absence of data. It was just because statistically you will have more women cooking in the kitchen because of our societal biases. This is another example of problems with representing data. So here I searched for politician because originally the example used to be CEOs. If you searched for CEOs, you would see all male images. And then people reported this, and I think Google changed the algorithm, so now you see women and males. But yesterday I searched for politicians, and you see only male politicians, mostly on the front page of search. And a search engine might argue that, we are just an indexing engine. Most of our data has male politician images, and so this is what you see. But as a society, we need to ask, okay, is this the bias? Is this a representation that we want to be fed back into the society? Or do we want to have a more equitable distribution when we're talking about various professions to fix for the gender gaps, let's say? Automated ad privacy settings is something I already talked about, where women were shown much more lower paying jobs, and this was a problem with the feedback into the system. You can imagine that if women are clicking on low paying jobs and men are not clicking on low paying jobs, then the optimization would just show women low paying jobs. Otherwise, nobody's going to click on those, right? So it's not that the algorithm is trying to discriminate. It is a feedback problem. Something, the way humans are interacting with the system is fed back, and then it amplifies that bias. And as we saw here in the predictive policing example, we have proxies on the arrest data. It's a proxy. It's not really the prevalence of crime. We don't have that data, and this is why we learned the wrong pattern. So proxies is another problem, and the key idea that I want you to take away from this is that the bias will be there in the data because we live in a biased society. But we don't want those biases to be propagated into systems that are making life-changing decisions for human beings. That's what we want to stop, and we want to avoid that. Okay, with that, let me get into the fairness metrics, which I think is the more exciting part of the talk, at least to me. So here we are asking the question, what is the effect of these decisions on my consumers, on the humans that I'm making these decisions for? And so Oliver talked about classification. Does anybody remember what classification is? Sorry, I'm teaching a course at Georgia Tech right now, and so I have this habit of putting people in the spot and asking questions. But okay, so here I have some triangles. There's some blue triangles, there's some red triangles. This is the apples and bananas example, and I just want the algorithm to differentiate between the red and the blue triangles. Okay, so I can make a line, and I can say, anything that's on top of the line is blue triangle, anything that's on the bottom of the line is red triangle. That's how the algorithm is learning to basically say, each of these triangles is a person, and the algorithm is deciding whether they should be hired for a job or not, whether they should get some loan or not, whether they should be left out on bail early or not. So what's the probability that they're going to reoffend the crime? Yes or no, should we put them in jail or not? And one could ask that, okay, let's say now I just talked about bias in data. So apart from triangles, we also have squares, which are a different group of people, and they're just represented, slightly shifted in this diagram. So I have some squares, and these squares are also blue or red. And my task is still the same. I want to differentiate blue shapes from red shapes. And what I can do is maybe move my my linear separator or classification boundary or this line and try to see, can I put it in an orientation so that I get most of the blue points here and least of the blue points that side. And one can ask a question, is it fair to achieve the highest possible accuracy in classification? Should that be the goal? Should you look to a machine learning algorithm and say, predict the best you can? Maybe that's the goal if you want to decide whether you want to put people in the jail, in the prison or not. Maybe it makes sense to do that. But let's say this is the best classifier. What about these people here? They are red people, so they were not going to commit a crime, but the classifier has put them on the blue side. And if we think about the recidivism example, will people reoffend or not? These people would not have reoffended, and we put them for longer in a prison, just because our algorithm was achieving the best accuracy. And this was the key debate, the key idea in the COMPAS debate. COMPAS is a risk of recidivism prediction algorithm that's been used by a lot of judges in the US that looks at a defendant, looks at the history of crime they've committed, and predicts what's the likelihood based on patterns of data that they will commit this crime again. And what ProPublica found, which is a leading organization in investigative journalism, and if you remember seeing Julia Angwin at one of the panels yesterday, this study was led by her. What they found was actually that African Americans were labeled as high risk more often, even if they did not reoffend, compared to the whites who were more often labeled as low risk, even though they did reoffend. And when we look at this table, we realize that that's a real problem. We seem like we are discriminating against one group in the population, and we are overly favoring the other group in the population. So one can ask, okay, is it fair to balance false positives? Maybe we want to not have false positives from one group and have more false positives from the other group, or like balance them. And maybe, okay, this classification boundary makes more sense because now I don't have any false positives. I don't have people who are mislabeled as yes. I don't have people who I mistakenly put into the prison. What's the problem here? What's a potential issue with this definition of fairness?
There's a false negative.
Yes. So if I look at all of these people here, they actually did reoffend. They did commit a crime again, and they were left out in the society. So society might complain, you left out criminals in my neighborhood, you are discriminating against those. So as you see, there are different stakeholders in this problem. Let's say the police care more about accuracy in the model. The defendants care about not having false positives. They don't want to be falsely accused and put in the jail or prison. And the society might care about who have you not labeled, negatively labeled incorrectly. Yes. Questions? All right. So in fact, there are a large number of definitions of statistical measures that we can play around with these positively, correctly labeled yes, correctly, incorrectly labeled yes, and so on. And you can have a lot of these. So there are a lot of research papers written on, okay, can you have sensitivity, can you have selectivity, can you have equal base rates at the same time? And all of these definitions come from a very different viewpoint, and different stakeholders have different ways of sort of rallying for the definitions, if you will. And so this is where we need ethics scholars and lawyers to tell us, what's the right definition to consider for a particular application. And this situation becomes even trickier if we start considering more general decisions, like where do you place an emergency room? You have a bunch of people in a city, and you want to decide where to place an emergency room, or you want to decide how much loan to give, or you want to decide how much deliveries you should schedule in a particular neighborhood. Let's go with the emergency deliveries. So let's say this is my group of people, some red and blue people. this is my emergency room, and I want to minimize the distance. So whatever distance people have to travel to go to the emergency room, that's sort of the cost for them to visit an emergency room. I want to keep that small for all of my people that I'm deciding this for, right? And let's say we have two groups of people, the blue group and the red group. So one can ask, is it fair to minimize the total distance that is traveled by any group? What can be the potential problems with this? Yes. So suppose, let's say even there's a class imbalance. So there's some minority, there's some majority group, and they're even distributed in a large spread geographically. Then if I minimize distances for the total distance for each group, the facility will move closer to all of this bunch of red people, and it will move much further away from that blue point, which is problematic. You don't want to make the minority suffer that much. So maybe we ask, okay, is it then fair to minimize the average distance instead of total distance? Because the numbers in the group really affected the total distance. So maybe we look at per person, what's the difference, a distance traveled, and then we minimize that in both of the groups, right? And then we can have clusters of populations, as zip codes are sort of highly correlated with the racial profile that resides in that. We can have clusters of populations. And then the average distance would actually place the facility between those two groups, making all of these people travel a lot more. And maybe in this case, having some sort of a different measure where you have some social services operate here might be a better idea than to harm a lot of penalize a lot of people who are in a cluster, right? So it's unclear again what the definition of fairness is. And there are in fact, so this is a paper from '93. And this itself says, gives some 20 different metrics of fairness. It argues for why each of those metrics might be fair. And this is a project we are working on in trying to identify, can we say some of these metrics are well aligned with each other so we don't have to decide between them, and so on. But it's a complex problem, and that brings us to the trolley problem of choice. So what's the trolley problem? Trolley problem says that you have, let's say, an autonomous vehicle that's driving, and if you leave it driving, it will kill 5 people. If you interfere, you can switch the track, and then it kills 1 person. So there's a lot of ethical debate on what is an ethical course of action in this situation. I'm not going to discuss that. You can read about that online. But I'm going to model that as a fairness problem. So now we have multiple definitions of fairness, as we saw, and there are at least 50 ways to be fair or argue that this is the right thing to do. And the question is, how do we decide? And one idea that I would like to throw in here is that for different corporations, they decide what their core value is, even when they're deciding what the logo's color should be. So as you see in this color chart, there are different colors, and each of these colors represents something to us visually. And when corporations are deciding what the logo of what the color of their logo is, they are making that conscious decision of what the core value is. So why cannot corporations also decide, or countries decide what their core value is? And maybe that can guide us make this decision consciously. And so the key idea I want you to take from this is it has to be a collective decision. Deciding what is fair, what is the right definition, has to be a collective decision that we arrive consciously at after a deeper dive into the application. So we need to understand, is it the problem in the data? Is it a problem of feedback? Is it a problem of representation? Are my variables proxies? What is the effect of decisions I'm making for my consumers? Is it unfair in some sense for some people or not? And to sort of hammer this point in, I want to look at this problem from this question from the perspective of various different research areas and argue that the voice of each of these is important in this decision. So for instance, a social scientist could tell us that, arrest data is not a good proxy. You should look at health data because people are more comfortable coming and reporting drug use if they want help from the doctors. Law or a policymaker could tell us that, don't use protected classes in your machine learning algorithms, because then you have disparate treatment problems, and that's illegal. Right? And then, for instance, this was the case with Facebook excluding advertisers, excluding people for advertisers based on race. And a computer scientist could say, or an algorithm designer could say, that, well, the knowledge of these protected classes can help us de-bias our algorithms. You see, if I'm looking at data and I know some are triangles, some are squares, I can use that information to make a fairer algorithm. So to not have disparate impact, we need to use protected classes and build algorithms that can incorporate the class of people. A statistician, for instance, can say that, you remember that big table from Wikipedia which had like all of those statistical measures? A statistician can tell us you cannot have two measures simultaneously. It's mathematically impossible. No matter what algorithm you build, it's mathematically impossible to have two different statistical definitions of fairness. And there's some work by John Kleinberg et al., Julia Chuva et al., Moritz Hart et al. So there are a sequence of works that defines what these different definitions are and when can you not expect them to hold simultaneously. For law, I think this is very important, because lawmakers cannot say that, how about you have all of those fairness definitions? Like, we don't want to decide, right? So it's really like, okay, one has to decide because mathematically it's not possible. An optimizer, if you will, can say something like, well, you remember the facility location problem where we had to place an emergency room and minimize distance? In that, for some data instances, so here you see Alameda County, we realized that there exist Pareto optimal solutions. So approximately good solutions irrespective of which metric you choose. This is some part of ongoing work that I'm doing with Akhil Jalan, Girija Ranade, Helen Yang, and Simon Zhuang. These are some very talented undergrads at UC Berkeley, and Girija Ranade is an assistant professor there. And so we can find some Pareto optimal solutions that might avoid the problem of choice. But we're not sure if that can happen for all data sets, for instance. And right, so again, to summarize, the kind of fairness we want has to be an inclusive story. We have to look at what different fields and areas bring to the table and how they can help us make a conscious decision. And here I want to say that I did not cover studies from economists, behavioral scientists, human-in-the-loop computing. And so let me just put a star, because there's a bunch of other areas that can contribute, some that we know of, some that we have not even known, and they might join the debate in the future. And to summarize, we looked at the bias in data models and variables from the predictive policing example. Then we looked at fairness metrics, the statistical and equity metrics for the groups. And then we looked at the trolley problem of choice, where we have all of these entities to give us some information of how to make the decision. And it's a short talk, so I could not even get to the problems with transparency, gameability, and interpretability. I'm happy to answer questions about these in the discussion, and thank you.
Thank you. Fabulous. So I know we now are machine learning experts, but for those who don't know it all, let's ask a couple of questions, both of Dr. Grau and of Dr. Gupta. So let me start with one. For our remote audience, we need to be on the microphone, so either I'll hand it to you or we'll repeat the question. So let me start with one of the hard ones, because all of us in data protection know that data minimization is a principle. You already mentioned the need for large data sets, and you talked a little bit about the need for data sets that maybe you didn't even know you needed, but were needed in order to have a broader picture.
Full picture.
Where do you see accommodating the pressure for, okay, but how do you actually only have what you need, suited to the purpose, so that we can recognize data protection principles? So let me ask you, maybe Oliver, from the product value, And Dr. Gupta sort of add in a bit on the bias and fairness. We hear about machine learning happening maybe on devices, so maybe it doesn't need to come back to a central area. Is that something that's going to be, the future, or is that for very certain, limited use cases? Please let us have some more on that.
Do you want to start?
Sure. Okay, so a lot of thoughts came to my mind when you were asking the question. I think the first is, I don't think that minimizing the amount of data is the right solution to the problem. I think understanding first, what is the algorithm learning? What is the pattern? Suppose the pattern is that, if somebody is disabled, you charge them more money. That's morally irrelevant. We don't want those patterns to go into algorithms. That's an issue. Privacy or protection of data is an issue. So if some algorithm is crunching all of this data and then using it to sell the data to some other entity and then make use of that data in some harmful way, I think that's more of an issue than minimizing the data. And the third thing I wanted to say was that I think so a lot of the algorithms are quite black box, if you know what I mean, right? Like, we don't know what's going on in a lot of proprietary methods. And in some cases, it's really the value of the algorithm that's running a company, so we can't even ask them to sort of display all the metrics in that. But having some checks on the algorithm, some ways in which auditors can check, like, okay, for these inputs, what are the outputs? Or if I look at the distribution of decisions, is that unfair? I think those are better ways of incorporating fairness into the system.
Yeah, let me try to answer your question in a different way. So I'm going back to my example, which is automated driving, which is something that is also sometimes considered a lighthouse application, because everyone knows how to drive and can imagine how difficult it might be. And on the other side, there's a lot of interest in industry right now, because people think it's really a huge gold mine almost. One of the key problems is safety. And so when is automated driving safe? This is something that is really hard to answer. So if you see what classically is done at automotive companies, yeah, they build real cars, and everything is then kind of finished prototype, and then they go out and test the car for either on special tracks or in the public. So now there are academic works, how many miles you have to, or kilometers here in Europe, you have to drive to test that a car, an automated car, is as good or better as a human driver. And the number, there are actually two numbers. One number is the lower number, is 240 million kilometers. So can you imagine how much that is? So you would need a number of cars to drive this amount to test the automated car is better than a human driver. The problem is automated cars are built with software, and software, you have releases, you improve your software. So what does it mean now? After every release, you have to test your car again. So this is one challenge. We need the answer to solve this, or the approach is to do it in a data center. Still, you need a lot of test data. You might want, here in Germany, we have a certification agency called the TÜV. There are other certification agencies worldwide. They have no concept yet, but I can just speculate. They probably will build up a computer with a lot of data to test that the vehicle is safe. So there are a number of data issues involved. There was also a good question from Jules. He asked, where do you do the learning, right? So at the moment, people think they do it in a data center, so under the control of the automotive companies or software companies. But you could also have learning on the car, right? And this would raise a lot of issues. How can you guarantee that the car is doing the right thing? The trolley problem is you mentioned. It's in my view, it's not a practical problem. It's also deliberately it's an academical problem. First, there is no correct answer. Yeah, because if you do your you use your lever. And you just kill one person, it might be ethical. People might say, yeah, it was the right decision. But actually, this is a crime. In Europe, you would go to prison because you killed deliberately with this decision.
An automated car?
No, I'm just saying there's no...
It has the pedestrian crossing and somebody jaywalking.
Yeah.
And you could kill somebody who's jaywalking versus kill the one who's pedestrian walking. Right, like it's the same manifestation of the trolley problem for autonomous driving.
There are many variations also.
Yes.
There's also this, does the system decide to kill one person or more than one person? I think so this is a very hypothetical question. The only lessons we can learn is you should not design systems that have some ethical optimizations in mind. But then, again, it's human factors. If you and I'm now reading these traffic rules a bit more in details. If you drive through a play street, which is an area which is not just limited in speed, they have these signs here in Europe. It's a play area. Whenever you have an accident, you have to avoid any accident. For example, with a child, right? That's the main point. But there are situations the child comes out from a corner you couldn't see. You are responsible. So what does it mean now? If you build now an autonomous car, what speed would you allow your car to drive? If you go to this, hypothetically, there might be a child coming out. The car would run like 1 kilometer per hour, which is I'm 5 times faster if I walk, right? So this is now interesting. What kind of risk are you taking, and who is responsible, right? This is always boiling down to these ethical questions. Who is also the liability, and this is really a tough one. And there's a lot of societal.
Let's bring in some of our eager questioners.
Sure.
So yes, in the back. Yes, let me bring it to you.
Hello, thank you very much. Are we on? Yep. Okay. My name's Carl Wiper. I work at the Information Commissioner's Office in the UK. And we're starting to do some work around explainability of algorithms. We're aiming to produce some guidance or a framework which will help organisations using algorithmic decision-making systems to explain the outcome of those decisions to the individuals affected, which is a very brave thing to try to do, of course. It's evident, certainly from the 2 presentations that we've had, that there are a number of ways in which you could try to do this. And at the moment, we're thinking of it from the point of view of the people affected, the people who are often the recipients of those decisions. There are a number of ways that you could do it. For example, people often think if they receive an adverse decision that there was something wrong with the source data, that it was incorrect or it was based on data that they weren't aware of, for example. So that's one thing to look at. Or you could look at counterfactual explanations of a decision. So you could say to somebody, well, if your income had been greater by X, then you would have been given this loan. Or if your age had been less by Y number of years, then you would have received a different treatment, or something like that. So there's a couple of ways that you could try and explain these decisions, but there are many more. I wondered if our speakers had any thoughts on what sort of explanations might be most helpful in that situation? I mean, I guess the answer is it'll depend on the situation, but if you had any general thoughts on the ways and what would be a useful way to explain this. And if I could just slip in an extra question on that as well, linked to that. It's clear, I think, from the examples in the second presentation that these are not simply mathematical calculations. The California policing example, for example, shows that what is affecting this is a risk appetite. The question is how many false negatives or how many false positives do you want, i.e. how many criminals do you want on the streets of your neighbourhood? That's really the question. And for many people the answer is 0, preferably. So that affects your risk appetite and therefore where you draw your linear separator. So do you think these explanations have to include those wider risk assessments which are essentially ethical judgments? Thank you. Sorry, it's long.
Well, maybe I start, try to be quick. So technically, of course, that's of interest to design systems. Yeah. If you have a technical system that uses decision making, and back to this automotive example, decision would be drive there and there, and if you are involved in an accident, that's where the engineer or whoever pays the bill, might be the insurer or the owner, is interested, why did it happen, yeah? And you have to, as a manufacturer, you have to show that you did the best possible technically and whatever. So explainability is a very important tool. And it gets more important because traditionally all these systems, they were model-based. You had a model and you could test it, yeah? And this is not any longer the case. So that's why we need more of these methods and tool sets.
Yeah, my name is Jeroen Terstegen. I'm a lawyer. And the sheet with all the equations, that's why I went into law. That's but very interesting to hear from an engineering perspective how this works, because as lawyers we deal with fairness. That's our core business. Maybe you have seen, what I wanted to ask you is, there was a study released, I think this week or yesterday, by MIT about cultural bias in algorithms and the lever problem. And there you saw various outcomes. One was that the French are more likely to spare the young if they cross the street, where the Taiwanese are more likely to spare the old if they cross the street. The Germans don't want to kill anybody, so your answer, I guess your German, is completely in line with how Germans look at this trolley problem. So my question is, how would you take away something that, because culture is so ingrained into society, and societies are then run by let's assume it's a democracy. What is fair in the law is ultimately decided in the democracy. So if you're an engineer and you are thinking of how to get rid of bias, and then there is cultures and there is legal systems and there's democracies having a bias, how do you solve that conflict?
Yep, go ahead.
So I think, as I said, like, we don't want these biases to propagate into the systems that we're building. We do hold machines to a higher standard than we hold humans. And so even if the studies show that ethically correct from points of view of different cultures would be different decisions, I think we cannot deflect the decisions of automated driving, for instance, onto cultural norms. They should not affect, we should hold machines to a higher standard. That would be my answer to this. And the answer to the explainability question, I really like decision trees because I think they're very easy to explain. If you did this, then you got this. If you did not do this, but you did this, you got this. I think that would be my favorite model for explaining decisions. There are also a bunch of other ways of explaining, like using submodularity. So people have used factorizing the decision into the most prominent aspect and the lower aspects. But one thing that one has to be careful about is, are these interpretations being used, could they be misused by people to game the system in some way? For instance, the credit bureau in US is required to tell people why they rejected a credit application. And they follow the other option that you mentioned. They tell people that, this was the aspect which was furthest away from our decision boundary in some sense. So if you could fix that, maybe you're closer to going to a yes for a loan application. And one question I think people are very interested in, at least from an academic perspective, is that suppose I queried a model multiple times and I asked, okay, for this person, why did you reject loan? For this person, why did you reject? For this one, why did you reject? Can I actually build that classifier? Can I actually find out what the algorithm was? And if I found what the algorithm was, maybe there are ways to game the system. So one has to be careful about how much you want to explain for it to make sense and for it to be useful for people. And then how much, you don't want to compromise the system while doing that. So those were the 2 points, I think.
Mm-hmm.
So I have a question. I'm Marlo Dominguez. I'm DPO at Erasmus University in the Netherlands, but I want to frame my question as a citizen. So I've been chair of my neighborhood for some time, and I was in constant discussion with my municipality because they wanted to implement some policy in our city, but the different neighborhoods in the city were actually very different, and they want one implementation of the stuff. So I think context is very important. So they talked to me, and so there were undesired and unforeseen effects of this implementation. And they said to me, well, based on our figures, this should be this and this and so and so. And I said, well, come to our neighborhood, and it doesn't work like this, the way you think. So my question was the contextualization of your question sometimes. So especially in your case, you mentioned 2 cases. Where should you put the emergency center? It could be that some people have cars and others not, or that there's a train or a tram, or these factors, I think they matter as well. And the way you present or frame the issue is they should have equal distance, but perhaps this is not relevant, but time is, or something else. And the other thing I wanted to say, just how you want to reflect on that. And the other thing is the classification of the fairness of classification. I think that what that was related to, would someone be do the crime again and so on. But was the and judges use the system. Is it the fact that if someone did do a crime again, that he or she will do it again? And is there a causality underlying in the decision tree? I didn't get that right.
Right. So very good questions, both of them. I think for the first question, a mathematician's answer would be, it depends on the way you define the distance. So I could say, how much time does it take for a person, given that they have a car or they have to walk? And this is something we were thinking in the context of the Alameda County. If you are in the Bay Area, you have to have a car to transport yourself. But maybe if you're a student, you don't have a car and you have to walk. So how do you take into account those factors? And so this was very simplistic. I did not talk about any of those factors. And for the second question, which was on, I'm blanking out. What was the second question on?
Was that actually a real prediction of future behavior?
Oh, yes. So yes, that's definitely a problem with the framework, right? You don't know. So all you know is people who were released, then you have some data on them for the next 2 years, whether they reoffended or not. You don't really know if the people, so if they were kept in the prison for longer, you don't know if it's because of that they did not reoffend, or if they were let out early, would they have not reoffended? So the causality is a big issue in these problems in an active area of research.
Thank you very much for the presentation to both of you. My name is Javier Lareo. I work in the European Data Protection Supervisor. And as far as I understand, fairness metrics are mathematics, so I mean they are clear. So would it be possible in real world to just make a standard set of metrics and just make public whenever you are designing or building an AI or machine learning system, saying, okay, this is our definition of fairness for this specific system, so everybody knows what you are considering fair, and then we as users, we as society, we as customers can decide if that's the kind of fairness that we want on that specific application or not. Thank you very much.
Again, a great question. Do you want to?
I might have a go. You might comment as well. But
Yes.
yeah, with many of the example cases we discussed here today, it's clear there's always some kind of conflict. Yeah. We had this trolley problem, which is an extreme problem, but it tells you you can't solve it. There is no right answer. There's always something, some casualty. So with fairness and with safety, you have to find compromises, because all these parameters are contradictory sometimes. Yeah, and this is really the challenge. And my answer as an engineer is, I can give you the mathematical tools, but it has to be solved by society. Society have to set, this is the standard, and we want this and this coming out of this, and we want this separately discussed and this separately discussed. This is my naive answer, because it's a very complex question.
Right. To add to this, I think in yesterday's discussion, it was also a point that was raised, which I thought was very interesting, that if you ask a 5-year-old what their ethical alignments are, and you say, I'm asking my consumer, I'm asking my customers, what is the fairness that they would decide, then you can't really defer that choice to them if they don't know what the options or what the implications of that choice would be. It's just like asking a 5-year-old. But having said that, there are definitely companies, like, let's say like Best Buy. If you go to the store, they say, if you find our product for cheaper anywhere else online, we are going to match that price and give it to you. And I think what you suggested is a very good option for different corporations. They could say, you know, this is the metric of fairness we are using. If you feel we have treated you unfairly, come to us, we'll remedy this in this way. And I think that would mitigate a lot of concerns. And that's I think it's a good approach. Yeah.
Thank you so much. Really, really gave us a flavor and hopefully opportunity to learn more. So thank you to you both. Please join me. Thank you. If you're interested in being added to the list to get the notice of the upcoming 7 programs, you have in your folder a little place to put your name and your email, or you can do it online. There is coffee across the courtyard for those of you who need a little bit of caffeine. And thanks to our partners at VUB and all of you for straining to really get our heads around this. Thank you so much.
And thank you for being a wonderful audience.
Thank you.